most of the week, and one is more connected to the previous talk right before this. So I'll kind of go through those two, and then I have a bunch of questions that I was writing to myself throughout the week, and I'll kind of pose some of them, and we'll see how it goes. So I wanted to start first with, I think I have a bit of a different background and perspective than a lot of the other people here. So I am a physicist by training. I'm now a computer science professor, but my PhD is in physics, but in experimental physics. So I worked at the Large Hadron Collider. I did machine learning stuff there during my PhD, but it's very much like, I feel like I'm coming from a much more applied angle than a lot of the talks maybe that I've seen. So I wanted to kind of talk about like how I got interested in interpretability, mech interpretability. I am doing some mech interpretability stuff in my lab right now, but I kind of wanted to frame it of like what motivates me to be interested in mech interpretability. So one of my like big driving questions is how do we build the most robust and efficient models? I mostly work on science models. I do now some LLMs and the agentic stuff for science, but I mostly look at scientific foundation models rather than like language models. But this is really one of my driving questions. Like I want them to be kind of maximally useful for physics. I want them to respect physics, like what's already known about physics, and really, I would say maybe one of my biggest drivers is I really want them to be efficient. I feel like a lot of AI development is a bit brute forcey, and we know that a lot of our models are over parameterized. So how do we build more efficient ones? And these are some of the questions that I think about, like why do some models outperform others? It could be architecture choices, learning mechanics. I mostly focus on the architecture choice side, so I'll talk about some work in that direction. Yeah, I kind of already said this, like why can we take a really big model and prune it down, but we can't build a tiny model in the first place? Besides just making bigger models and adding more data, how do we make models better at what they get wrong? And then I'm really interested in this last one. Do models learn physics? If we're trying to do physics tasks, do models actually learn physics, physical principles in order to do those tasks? And if so, like when, where, and how do they do that? And then, you know, I think for a lot of scientists, the last question is really like the dream of, we think if AI models are doing better than what we built by hand to do physics tasks, then maybe they're learning something new that we don't know about the universe, and we really want to get that thing out of the model. I don't think anyone really knows how to do that right now, but this is kind of like a quest in AI for science, I would say. Okay, so I don't want to spend too long on this stuff because I want to get more into the discussion, but I'm going to show some results from my lab. So we spent quite a while thinking about this idea of like, is inductive bias useful for doing physics? There was, I feel like people have moved on a little bit, but for several years there was like this big fascination in the physics AI community of like, we just have to make every model symmetric or equivariant in some way, or based on kind of symmetry. Physics is super symmetric, so obviously like we're going to get the best models if we do this. So I was really interested in this question, and so we kind of tried to first think about like, what do we mean by better if we're saying we get better models? So obviously one thing is accuracy. Do we get more accurate models? But we can also think about like, do they learn to generalize more quickly or better? And are they more efficient, both in terms of model size and the amount of data you need to train? So I like this idea of using physics as a sandbox. I'll come back to this. So this is the idea of like taking physics tasks or physical systems and using them to kind of study these questions about what models work better. So we looked at two particle physics tasks. I'm not really going to like get into the details, but one is kind of a classification task, and one is a trajectory reconstruction task, basically. So the first thing we did is we built our own kind of version of a tunable semi-equivariant graph neural network. So a lot of these results are with GNNs and not transformers. I'll talk about transformers in a minute. So basically what this architecture allows you to do is it has separate information flows of equivariant information or equivariant messages, and then a separate stream which is just a regular GNN, and then you can mix these together at the end, and you can kind of do like a hyperparameter sweep, tuning the kind of weighting or amount of equivariant information versus non-equivariant information. You can turn one off, turn the other off, to recover like a fully equivariant or just a regular GNN. And then we looked at like what combination gives you the best results, and we found, so like in both of these plots, the lightest color is the best. So we found, so on the left is accuracy. Obviously, like bigger models tend to work better, but we find that a combination of equivariant and non-equivariant information gives you the best model amongst, like the biggest models in general tend to be best. Amongst those, mixing equivariant and non-equivariant information is best. We also looked at this thing we call ant factor, which is basically the ratio of accuracy to number of parameters in your model. So like small ants are like small and powerful, it's cute. And we found that we get the most efficient models also by combining some amount of equivariant and non-equivariant information. And if you just do one or the other, you lose some efficiency. So then we did like a little bit bigger study. We looked at a bunch of different kinds of models on those two. I'm sorry, those results were for the classification task. So then we looked at a bunch of different models for that jet tagging classification task and the trajectory reconstruction task, some of which were like industry standard models. Obviously they're not anymore, but some were industry models, some were physics specific models, ranging from transformers, CNNs, GNNs, deep set architecture. This one's a linear discriminant on like a really clever physics basis. And then we looked at a bunch of different equivariant models as well, which use different ways of enforcing equivariance basically. And here we're looking at equivariance to the Lorentz transformation because we're dealing with relativistic particles. And then we looked at, for the trajectory reconstruction task, this is like the previous state-of-the-art model that we built years ago now during my postdoc. So it's a message passing, GNN, interaction network construction. And then we also looked at a rotation equivariant trajectory reconstruction model, which is rotation equivariant in like the 2D plane of the detector. Our detector is a cylinder, so we don't have 3D rotation equivariance, but we have 2D rotation equivariance. So then we looked at rough patterns in these different like metrics of goodness. We found that overall it's really hard to draw a clear picture between accuracy and the presence of equivariance enforcement or not. The best performing model is an equivariant model, but they're all like actually quite similar in performance. They also have a bunch of other design choices that differ. Like the only thing is not whether they're equivariant or not. They use like different graph constructions. They use slightly different information from the particle collision, so it's a bit hard to like isolate the effect. I think the most interesting result we found is that it does not seem to help model efficiency. So if the by far the most efficient model is that really cleverly designed basis model. So it seems to be maybe, at least in this case, more of an effect of the way you set up your data than anything to do with the model itself. Basically, like how much information can you directly and cleanly encode in your data set leads to more efficient models. In the tracking case, in the trajectory reconstruction case, we actually saw that it did for like very, very small models, equivariance helps both in performance and efficiency, but as soon as you add slightly more parameters, the story flips. Generalizability and data efficiency seem to be impacted pretty directly by the enforcement of equivariance. The only caveat here is that how you do the equivariance enforcement seems to matter somewhat. They're depending on kind of how many, what kinds of approximations you do when you're setting up the equivariance enforcement, you can get slight variations in generalizability. The best one is using the irreducible representations of the symmetry group to parameterize the learning space of your model. That's also computation more expensive and more difficult than just constraining the message that's being passed in your GNN, but it does lead to better, more complete generalization. And then, yeah, data efficiency makes sense. If you are giving some information to the model before it's learning, you need less data to get the same level of performance. Okay, so that's kind of one way we thought about it. It's not really interpretability, but it's trying to probe a little bit of what matters to good performance. So now I want to talk about some of the mech interpretability work we've been doing recently. So this is led by one of my students, Daniel, who just finished his undergrad as a math major. He's amazing. He's also looking for, to plug him, he's looking for post-bac, pre-doc, internship kind of things. He's really great. If you're interested in hiring a student. So these are some of our recent results. So we're looking at a transformer trained on, again, particle physics data, trying to do different, you can attach different types of heads to do classification of particle objects, regression on different kinds of physics objects to predict their momentum or different qualities of the particles. These results, I think, are all looking at classification heads. So first, we're okay, I guess the kind of mech interpretability questions that we're asking are really motivated by specific behaviors that we want to change in the model. So one big thing is that, of course, our AI models are not perfect. They still get things wrong. So one of the big things that they get wrong is there are certain kinds of particle decays that look really similar to each other. Their physics processes are similar. They produce similar decay products. They have similar kinematics. So they're, of course, really hard to distinguish from each other. And we can see that, for example, the WQQ and ZQQ, those are two different particles, but they're decaying to the same thing. So the model mixes them up. This makes sense, right? But we want to try to get better models, so can we intervene to try to make this better? Daniel picked a few results from that kind of confusion matrix, specifically looking at Higgs to gluon-gluon jets that are misclassified as what's generally a background process. So these are really common and non-interesting things that we generally want to throw out of our data, but something really interesting, which is a Higgs boson, is being confused fairly often for these non-interesting things. So he decided to focus on that, and we want to look at are there ways we can get the model to be better at this task. So first we looked at, can we separate the correctly classified Higgs jets from the incorrectly classified Higgs jets somewhere in the model's activation space. So first, he did a linear probe to try to predict whether the Higgs is going to be misclassified or not, and then look at how accurate that probe is in different places in the model. So this is just a plot of the probe. It's not very interesting. Except you can see that pretty early in the model, so I think there's 6 transformer blocks in this model, pretty early in the model, they're easy to separate already. So the model is like learning to, like the model is treating them differently pretty early on. Then he went layer by layer and extracted this class token, which I probably should have shown the model architecture, but the class token is what's used at the end, fed to the classification head to do the final classification prediction, so it's like updated in each transformer block. He looked for where in the model these Higgs jets that are misclassified become more similar to their incorrect class than they are similar to the kind of embedding space of the true Higgs class. And like this is pretty interesting, I think, the left plot. So we see that between layer 5 and 6, there's a flip. So these misclassified Higgs jets are maintain pretty close similarity to like the average embedding of the correctly classified Higgs jets until transformer block 5, where we see this behavior switch and they start to look more like the average embedding of their incorrect label. So he looked at this idea of layer 6 kind of being a rejection gate, where you're having some kind of like causal impact on the Higgs jets being misclassified, and then did a really simple ablation study, right, to look at like what's the impact of skipping this layer, and we actually recover some of those jets that were misclassified if we just skip layer 6. Obviously, this is probably going to have some kind of other, like, just doing a removal ablation is very brute force and like not what you would actually do for a useful intervention, because probably it's going to make some other classification worse. But we're just trying to explore some of the mechanics in the model. Then we also looked at, like, is it the whole transformer block? Is it just the attention head? Is it just the MLP? And it appears to be like a combination of both. If you just ablate the attention head or you just ablate the MLP, you don't get that same kind of rejection gate behavior. So it seems like, you know, something's happening with the whole block. Another thing we looked at that I feel like is the most, there's very few papers on mech interpretability of non-language models, and especially like science foundation models. There's like one other main result I know of that's similar to this, but we looked for steering vectors. So are there like directions in the embedding space at different layers of the transformer architecture that let us steer one type of jet into another type of jet? That as a steering vector isn't actually that useful for identification. I'll talk more about what we ultimately want to do with the kind of steering vectors. But we did find a really strong steering vector for changing like background jets. So QCD jets are just what's produced in any particle collision. They're not like interesting signal to us. We found a steering vector that can change basically any interesting jet to look like a background jet. By intervening on that activation, it's an activation vector in layer 4, or sorry, transformer block 4 of the model. So this indicates, at least approximately, that jet class identity, at least signal versus background, is encoded in the residual stream of the model at layer 4, and that you can intervene on what the model thinks a jet is without retraining it. There also seems to be like a really important attention head in layer 0, head 4. Our idea is that this is potentially part of some kind of larger circuit that we're trying to identify, because it has like an effect on a lot of different jet types, but it's very distributed, so maybe there's like something physically interesting happening. that attention head and looking at the attention over different jet types of that attention head, and it's parameterized by particle position, which is order in which we're processing a particle, which normally wouldn't be interesting, but we order all of the particles in this data set by momentum. So this is basically a momentum distribution. So we're seeing also that this attention head seems to be focusing on like particle momentum as a useful feature. Again, this is not super precise because like, right, we're looking at particle order and not actual momentum, so we need to like do the x-axis to really get a clearer picture, but maybe hinting something like about what this attention head might be doing, which is something we're trying to do now. Is like, okay, if you find an interesting attention head or an interesting circuit, like what is it actually doing in a physics sense? Can we decode that at all, or is it just like, oh, there's a circuit that correlates to this, we don't need to or can't understand what the circuit's actually doing. So the like downstream interest that we have with this is, can we intervene in some ways to reduce the negative behavior of these models without training yet another new model, without doing fine tuning. There's issues with fine tuning, right? We know that it can introduce like forgetting and other things in models. So can we do a causal kind of intervention instead? This classification is one of the problems that we're looking at, but what I think is the most promising potential direction of this work is that when we're building physics models, they're almost always trained on simulated data, because that's where you have ground truth, right? You can simulate a particle collision, and you can tell the simulator exactly what you want to happen. When you're looking at real data, you're using algorithms to try to infer what happened. Obviously that introduces noise and uncertainty, so we usually train models on simulation. However, as many of you probably know, physics simulation, to do it really well, especially of a really complicated, like multiple physics process system, like the Large Hadron Collider, is incredibly computationally expensive. So usually we use a simplified simulation that is close to nature but doesn't actually match nature, and then we end up with this problem where we build a lot of cool AI models that work really well in all of these lab testing cases, and when we try to use it at the LHC, it's garbage. So we are looking into trying to identify like steering vectors or circuitry that would allow us to like move simulation like to look more similar to real data, and hopefully improve the model's performance on real data. We're also really interested, I'll come back to this persistence question in a little bit, of looking at the persistence of these kinds of mechanisms. Like, can you just identify things in one model, and then if you use a different model on the same data set, same task, the mechanisms disappear, or are they persistent? I'll come back, like, I saw someone put the platonic like, universe idea on the discussion list, so I'm going to come back to that in my like discussion questions, but I think it kind of relates to that concept. The last thing I'll mention in this direction before getting into stuff related to the last talk is this planned experiment that we have coming up, which is I think a really exciting, cool physics sandbox experiment. I'm going to kind of skip this. So the LSST, the new Space Observatory experiment, is coming online right now. It's taking pre-commissioning data. Right now, my co-PI is one of the leaders of the experiment and the director of the LSST Discovery Alliance, which is like a nonprofit research group that basically runs the LSST and does a bunch of other exciting stuff. So we have this planned like 4-year sandboxing experiment where we have like a really interesting chance to see how models change as we get new data like over time. and we can control how that data is collected. We know what the observation experiment is, and we have these existing astro foundation models that are trained on other astronomy observation experiments, so things like ION from the polymathic group, which is trained on a bunch of different astronomy experiments, and Star Embed, which is like part of the NSFAI Institute on Astronomy Sky. It's their time series foundation model. So we'll be using these, also building our own foundation model specifically for LSST that we're continually updating as we get new data from the experiment. So we can ask questions like, how do rare objects, for example, move in the embedding space, or how does their representation change as we add new data? What about when we add it to when we have data just from one experiment versus adding it to these models that already like have some embedding of astronomy and have different data represented? How do models handle multiple observations of the same object from wildly different experiments? Like, are they able to automatically match these in embedding space? Do we need to intervene somehow? Where does generalization emerge? Like, is it dependent on the architecture or the amount of data? Like, when does our LSST foundation model start to generalize across rare object types, or to out of distribution data, or to data from other experiments? And then on the mechanistic side, like, are expected astronomy qualities learned in the model? When are those learned? Do you just need a lot of data? Or do you need more diverse data? Like, when do these does it even happen at all that it like learns conservation laws or not? So a lot of really exciting questions that I think we're going to be able to probe with this setup, which is why I think physics data is like so fun for studying these things, because we have so much control and like insight that we don't have in the internet language that a lot of foundation models are trained on, right? Now thinking a little bit about the previous talk before this. So a lot of this work is led by Nathan, who's here, so he should also say things during the discussion. But we are thinking a lot about, okay, lots of claims, results coming out that we can just automate science. What does that mean? How do we know if we can do it or not? How do we evaluate it? All of these kind of things. And I will say, like, I'm a very interdisciplinary researcher. Like, I think some of the questions that came up in the previous talk about, like, can we write metrics for X, Y, Z, are actually incredibly complicated questions. Like, Nathan and I collaborate a lot with like philosophers of science. You know, these are things that are not new. People have been thinking about them for a really long time, and if you really dig in, they're actually like quite complicated, I think. So I want to start a little bit with like some literature that's really grounded how I don't want to speak for Nathan, but maybe Nathan as well, have like grounded how we think about measurement and how you can evaluate really broad claims about like agentic systems. So I think measurement actually incredibly difficult. And I'm going to show some different reasons why I think measurement is difficult. So one, figuring out what to measure is hard. Like, we like the idea of writing down metrics for things, but like, what metric are we even trying to come up with? How do we know if it's right? This is very difficult. So one of my favorite ways of thinking about this, one of my favorite papers that I'll get to in a second, takes inspiration from this Sesame Street book called Grover and the Everything in the Whole Wide World Museum. So in this book, Grover goes to a museum that says it's everything in the world, and he goes to different rooms. He goes to the tall hall, where it's all the tall stuff. He goes to the room of all the vegetables in the world besides carrots, that has all the vegetables. Long things you can write with, like lots of different categorizations of objects, right? And then he says, he's gone through the whole museum, and he's like, okay, I've seen a lot of things, but I still don't think I've seen everything in the whole wide world. Where did they put all the other stuff? Where did they put everything else? and then finds, oh, the everything else door, and it just leads outside to the actual world, right? So I think this is like a really cute, kind of intuitive framing of like, we try to box things when we do AI evaluation, and often by creating these boxes, we're like applying some kind of simplification to the actual world and the actual system. So this is the paper that like took inspiration from this book, AI and Everything in the Whole Wide World benchmark, and it looks at how we make benchmarks for AI and whether or not they are actually measuring what we claim or represent them to be measuring. One of the examples that they talk about in the paper is ImageNet, which was, as many of us know, like the gold standard of computer vision evaluation, right? It was the most these are quotes from the developers in their publications. It's the most comprehensive and diverse coverage of the image world. It's an attempt to map the entire world of objects. There's lots of different classes. This is just a tiny example: food, dogs, fish, furniture, etc. But if you look into the actual distribution of categories in ImageNet, you see like almost 100 classes are different kinds of dogs, right? We have kind of varying things like electric guitar, flagpole, fireboat. There's like New Zealand beach is a category, and do I have this slide? Right, so this is a quote from the paper. The way that they built ImageNet originally is they looked at this WordNet ontology, which was a previous like linguistics project that was trying to develop a tree structure of like categories in language, and ImageNet developers were like, okay, well, this is a list of categories that someone built, like that's nice. I'll just use those categories and I'll find a bunch of images of those categories, and then boom, computer vision, right? As soon as we solve ImageNet, we've obviously solved computer vision, but there's much more images in the natural world than just this like WordNet ontology. It was a project developed not for computer vision or even vision or images at all. It was like a linguistics project. So I think this is a really nice, tangible, familiar example of like, it's really hard to actually set up benchmarks that measure the real thing. And that's okay, but if we start to obfuscate the difference between the benchmark construct and the claim, like natural images, then we start to kind of blur the picture of what we're actually learning about our models. Okay, even if you know what you want to measure, figuring out how to measure that thing is difficult. So Nathan and I think a lot about these ideas of validity in AI evaluations. There's a nice recent paper that kind of puts together different concepts of validity. When you're thinking about measurements, so you have content validity. Does your evaluation cover all relevant cases for the thing you're trying to measure? You know, criterion validity, like does your evaluation correlate with a known evaluation that you trust? I think we think a lot about construct validity. Does your measurement actually measure the thing you think it's measuring? Does it capture the construct of what you're measuring? Can it differentiate between constructs that should be different in your measurement? External validity, does it generalize? Consequential validity, is it grounded in real world practice and how AI models are actually used? We're also looking at some like psychometrics, views on evaluating benchmarks or like meta-evaluation. So are all things in your benchmark equally difficult? They all measure the same construct? Do all models view them as equally difficult? There's a lot of like insight, I think, from psychometrics. One of my other PhD students is psychometrics researcher, so I think there's a lot to be drawn from there. And then lastly, describing a measurement, also very difficult. This is from the same paper. kind of giving an example of when you talk about measurement, you say what you're trying to measure, what your claim of measurement is, and then what you're using to support that measurement. And they kind of show an example of like a reasonable and unreasonable measurement description. So like reasonable, you might say you want to measure arithmetic accuracy. You claim model A can be used as a calculator, and you support that by saying high standardized math scores implies high arithmetic accuracy. That's fairly reasonable. Often we do things like the second, which is we want to measure intelligence, we want to measure reasoning, we want to measure these very general things, and we want to say model A is intelligent, model A is AGI, model A is a scientist, and we do things like saying having high like International Math Olympiad problem solving implies high intelligence. That's like quite an epistemic leap. So Nathan is running this really interesting set of work on how do we try to benchmark scientific discovery. We start with the idea that scientific discovery is like too broad of a task to be easily evaluated. It creates a lot of obfuscation in the mapping from like construct space to evaluation space. So one of the papers he wrote in this area is a suggestion on how to think about building a benchmark for AI scientist evaluation. You kind of take the overarching task, you split it into human interpretable subtasks, and like we can talk about this more. I think all of these should be informed by like human-computer interaction type of studies, like how do scientists actually think about this blue level, like are they separated, are they feedback loops with each other, like this is a simplification of the math, so don't take it as like gospel. And then those things still too hard to evaluate agents or LLMs on. So we need to think about actually measurable tasks that sort of that are some parts of these interesting high-level tasks that we care about. And then I think it's impossible to prove maybe that AI can always do scientific discovery. You sort of can only, and I think in a lot of these very complex, like reasoning, intelligent type of evaluations we want to do, it's very hard because we don't have a definition of intelligence to say yes. But I would say this is a bit of a flip where we can say, okay, if it fails at one of these reasonable LLM executable or measurable tasks or agentic measurable tasks, then it is not completely doing literature review. That doesn't mean if it gets perfect scores on all of these things, then like it can do scientific discovery for sure, and we should just like let AI run science. But it at least gives us something to probe. This is a recent paper that is hopefully going to be at ICML, we'll find out in a week. But it's on the Philosophy of Science archive already. And we talk about this idea of scientific alignment. So this is quite getting away, I think, from the interpretability focus of the workshop, but ties to the previous talk. So we took, at the beginning of this paper, like a big step back from the technical side and said, what is science? This is where we brought in the philosophy of science collaborators, and we say, we believe science is a system of knowledge production and an epistemic social system. So if you're just producing information, even if the information is correct, which is obviously a big question that we need to evaluate, if we're just producing a bunch of correct information, but the volume or complexity is too big for humans to update our collective understanding of science, then it's not really doing science. It might be a tool. So we talk about the idea of an oracle in here. If you have a perfect AI system that gives you true information, that doesn't mean that science is solved, in our opinion, because we still need the human understanding piece. So an oracle could be a tool for doing science, but just having a bunch of correct results, if you can't interpret them, you can't make connections between them, that's not really what science is. So we think about ways to support the epistemic values of science, like traceability, verifiability, calibration, coherence, and intelligibility in the design of our AI system. So not saying that like you shouldn't use agents for science, but how can we design agents, agentic systems that actually support the things that you need to do science productively. And we talk about different research directions in the paper, things that could be drawn from technical alignment and sort of adjusted for science. A lot of HCI studies, like I think the big missing piece in a lot of what we've been talking about is like you need to know how people actually use these models in practice. Like I like you said like, oh, send it to your friends. Like I think we need to be doing things like that. Obviously it is expensive, like that's the thing to think about, but like we need to be seeing how people actually use these things in order to make any kind of conclusions. And then also we need to think about our social systems of science, like peer review is collapsing or dead. What do we do with that? Yeah. Oh, that's a copy slide. Okay, so I've talked for a long time. Here are some questions that I had. So one, I see sort of two paradigms in the talks that I've heard here. One is like we can do really precise mechanistic work in toy models. We can identify lots of like very precise circuits and mechanisms, or we can do kind of more general predictions like phase transitions, scaling regimes, these kind of things on actual frontier models. So like how do we interpolate between those things? I don't have an answer, but I would love to discuss. And particularly I was thinking like in physics, we use toy models when we have a good idea of how the toy model generalizes to the real system. Is there something like that in machine learning? Like the modular arithmetic to Gemma to Claude is like some kind of universal class? I don't know. I thought the task composition, I forget which talk that was, but that was really interesting. How do you pick a basis to do interpretability over? Like, I do it in physics because physics has nice bases. In language, the picture is pretty messy, right? We have hierarchies, kind of. We have constructs, kind of. There's lots and lots of exceptions to all of the rules that we might write for language. So how do we pick a basis to evaluate over for interpretability in language models? Is like, you probably can't write down a complete basis, so is like safety relevant, a useful substitute for complete? Also, like, there's a lot of power and political kind of questions in like deciding what the right basis of evaluation is. What do we do with these like sort of approximate interpretability results? If we squint, it looks like this. I mean, to be fair, lots of our results that I showed of the like jet transformer model are like, it seems like this is physicsy, but like how do we build a complete theory or a more complete theory from results like that? What are our standards of goodness of interpretation? How do we verify them? Especially when it's harder to run experiments in like the real world on language, on people, than it is to do it on particles. Like, are any mechanisms persistent? I really was struck by like the arithmetic heuristics in the talk yesterday. Like, are they always used when the model is doing arithmetic? If so, like, then why doesn't it get all the arithmetic questions right? Like, is it, like, right, how often are these mechanisms actually used? Do they exist across different models? Do they come from the training data? Is there some kind of platonic universe of representation? Like, this idea has been coming up a lot in physics recently of, like, is there a true embedding space of images, for example, and all of our models are approximating that, and there's results like you take just an image, like a frontier image model, and you put a bunch of astronomy images into it. The way they end up in embedding space is quite similar to where they end up in embedding space in an astronomy specific model. So like, does that mean there's a true manifold and we're all trying to find it? I don't know. And then getting more into the philosophy side, but like, what do we want out of interpretability? Should we expect things to be interpretable? Like, you know, in physics, we love beauty. We want the universe to be nice and distill it into nice math. Like, is it reasonable to expect that language can be distilled into interpretable math? And then I'd really like to hear thoughts on what's the connection between interpretability and safety. Is the idea that we can stop all of the behaviors that we don't like in a provable way. That's kind of how I think about it in physics, but I'm curious how you all think about it, and like, does that impact what kinds of questions and approaches we ask? Yeah, so the rest of the time is open. Yeah.
And can I ask a question?
Yeah.
I'm not sure I understood the difference between like the second point and the first point. Like, is the maybe I'm not entirely understanding what the question is here, but like that if we have like mechanisms that work in toy models, we would like to extend them to real world models in some sense. Then I don't. Yeah, I guess that.
So all the results, and I'm not like as in this as some of you are. This is my interpretation of the results that I saw. There are toy experiments where we can get like really precise circuits. We can't find those precise circuits in like billion parameter models. There are interesting results like the phase transition prediction talk yesterday that we see repeatable patterns in toy models and large models, but that's not as like precise as a specific circuit, right? So like, can we like make circuits more generalizable? Is that even possible to do? Is it computationally intractable? Like, I don't know. Are these the same kind of results and something's just missing to connect them together? Like, yeah.
I guess I have some thoughts on that.
Yeah.
Yeah, I mean, the way that I see it, a lot of it is bottlenecked by a greater theory of data. So like, in particular, like when we talk about toy models and toy tasks, like the modular arithmetic is one that's like well studied. But you know, if you look inside of a transformer, like let's say you're a transformer and you ask it to do modular arithmetic, like we don't expect there to be like a Fourier representation inside of it. Yeah. So yeah, it's like embedding these like particular toy tasks, almost like separating toy tasks from like toy models. If that makes sense. So yeah, like having like a zoo of different toy tasks, which are of different complexity, which give us insights into what particular properties, into just themes in how models learn, that could potentially feed into like a greater theory of data. And that's like one route of progress I like.
Yeah. And maybe this is really neat. Like, why do we not expect to see the same kind of like Fourier representations in big transformers that we see in like the toy models?
We do see the heuristics yesterday were the same.
Right. So then why is it wrong sometimes? Like, why does it get arithmetic wrong?
Wait, if you train if you look into like 4.6.
Well, the talk yesterday was Korean ones. Yeah,
That
yes,
was-
we do, yeah. And like also, like if you look at my arithmetic, yes. Like if you look at our paper,
What do you mean? Like someone looking to mechanistic?
Yeah,
I don't think Max's talk was on state-of-the-art models, right? I don't think Max's talk was on state-of-the-art.
No,
No,
I'm
that's Young Thomas.
Yeah, I can stop, I
Yeah.
have Korean ones.
Oh, okay.
I think the problem with quasi arithmetic is that if you want like quasi arithmetic is like a bounded thing, right? So it's unlucky. The problem with general models is when you try to generalize to longer to like something longer numbers, maybe you're not. So that's kind of like a different problem.
Yeah, I think also in a sense like, when you train an NLP on a very, very specific task, you're just like doing that one thing, it's like a super bounded problem. Meanwhile, like this bug of heuristics seem to come in, when you have this general model and you're trying to do like kind of any operation. So I think it's just like one problem is very small and you have a constraint architecture to learn that one thing only and you test it on that one thing only.
Yeah, I think that is the bigger impact.
Because yeah, I guess that if you try to do multiplication on something with like a modular addition, it will make mistakes.
Yeah, well, so can we ever expect general models to be perfect at any task? Like, I guess that's like something I think about a lot with like, with the math examples, right? Like, yes, I know the explanation is that it can't do math on numbers that it doesn't see very much. So like, then that to me means it's not learning math.
It's not noise that doesn't see, it's like if you give me two 10-digit numbers and I multiply in my head, I'll make mistakes.
Yeah.
And like in this way, numbers are not different. Like there are many ways which they are, but in this way, like they're using some kind of like heuristic algorithm that they like kind of like.
And you tell them to use the correct algorithm to multiply 10 digits in however many steps.
Right.
Just like if you ask the human to do that in however many steps, they would do it. They just don't want to do it most of the time.
But in Jonathan's talk, it didn't even get simple arithmetic right every time. So it's not just that like these are harder problems and. Sorry?
Those weren't state of the art.
I don't know, like if you have a larger model, I don't know if it's qualitatively different. Maybe just memorize like as many heuristics more, and at some point approximately it just goes beyond a certain threshold by which this is effectively doing perfect.
Sure, but if you like ask somebody who like I've never like tried like thought about numbers they'll be they'll say they'll make like they're like very elastic.
I think we're talking about different things though. There's like the problem of completeness of our models,
Yeah.
and then there's also the problem of correctness, and those are kind of orthogonal when we're thinking about what models do.
Yeah, so I think like it's not surprising that like they make mistakes.
Yeah, and I think more importantly than building a perfect model is being able to quantify the error and bound, especially for
Exactly.
safety, is being able to say like, I know the bad thing is only going to happen a very small amount of time.
I also wanted to add from like Zara's talk that you still need to like fine tune it, like for the arithmetic example specifically, that you do need to fine tune it more as you're increasing like the number of digits, but in like log number of samples rather than or digit something rather than linear, which is like
This is for a target.
for what?
For targeted model that does multiplication, the multiply numbers for estimates. Yeah.
So if I may add though, right, like when we're talking about modular arithmetic, like between humans and how it's done in models, like you're operating at different logic levels, right? Because when you talk about having the models do it, right, you're like, this is the equivalent in humans to have, like asking it to be baked into our synapses, how to multiply 10-digit numbers, right? Whereas in reality, we have like these abstract symbolic representations that have this like self-corrected mechanism and they like associate in some very complicated way that allows us to form like these abstract rules that we can like implement generally, right? And these are like fundamentally distinct things.
Yeah, so this is something that I've been really curious about, 'cause like I'm not from the learning theory side, is like there's if I'm like understanding right, there's an implicit assumption that like human and machine intelligence are connected, right? That like, 'cause like I mean to say that well, yeah, humans wouldn't do this perfectly either. It's hard when numbers are big. Like, that's that's like a big epistemic statement, I think, on
I mean, like, the thing for me where that's coming from is not that perspective. It's that some people say, oh, language models are stupid because they can't do this. And then I'm like, oh, I'm stupid. Like, and that it's more like an argument of like, oh, semantics and intelligence, as opposed to what you're
But it's
saying.
also like more mechanistic sort of explanation, right? Which is like how much loss decrease, how much concentric decrease is doing 10 digits multiplication, like compared to all the other things that you need to get right.
Meaning that you would get a better score if it did it wrong.
Exactly. Yeah, that's true. Not if there is an RL afterwards or something. Yeah. Also, the other thing is like the heuristics are algorithms. Like but it's kind of wrong to say that the heuristics that the model used to multiply 10-digit number. If you ask them to what is the ballpark if you multiply this to 10-digit number, they apply the right heuristics and give you the right ballpark in the same way that humans would. Right, and those are correct. Those are algorithms. I don't know why we don't call those algorithms.
I also think like maybe another like blurriness that I see is these are all trained, like to say that like is the same ballpark the same way that a human would, like also it's only trained on what humans would do, right? So is that connection valid, I guess, to say that if we showed examples of how we think, then it will organize the same way that our brains work?
But maybe this is a question of like, I don't know exactly how to say this. I want to say scale, but that's not really what I mean. It's like we're trained on human data also. Yeah, but yeah, maybe I'll just say that. We're also trained on human data. Like we got all this stuff in, but our brains are doing something that is not exactly what the our emergent actions in the world are doing.
Yeah, I mean, I guess the scale, I would say, is that like it's about low resource versus high resource learning, right? Like humans are excellent low resource learners. I mean, okay, you can say that the amount of data that we have for like visual perception is high, but like in terms of like actual textual things that we like learn, it's much lower than a large language model to accomplish the same tasks. So I think there is like a difference in paradigm between those. I guess like that's sort of
I mean, we created language. Like that was like we were the right machine for that. Transformers are not meant to be the right machine for language. Also, arguably, we're born pre-trained.
Yeah.
Like,
wait, what do you mean?
we are born pre-trained. Like meaning like you have the structure, you have those synapses. Like when you're born. Like when you let me say. When you're 6 years old and you get to school, you're for sure already pre-trained. And then like if you're a smart kid, school is just a fine-tuning.
There's a lot of time.
Okay, I sort of see what you mean.
What?
There's a lot of time between 4 and 6.
There's a lot of like genetics. Like there's a lot of like brain that you get through genetics. And then like when you say we're like very efficient learner. Well, if I've never showed like the best vision model a stop sign. Actually I unlearned the stop sign and then I show one stop sign. I never done these experiments, but I bet my very low net worth as a postdoc that it learns everything of a stop sign with like few images. That's what I'm saying. So it's like I'm not sure you're comparing.
No, but I think we have strong evidence for this, right? Like, the difference in compute between like a model that can speak like a 5-year-old, which probably already saturates on the genetic, right? Like advantage that the brain has versus one that can like I don't know, right? You can do research on a grassroots level is larger than the difference in compute between a 5-year-old and like a PhD student.
Well, but a 5-year-old is not using well a brain that has potential. It's not like
but like if you just like kind of
what?
I feel like this is missing a bit of like biology and brain like it's not just that it's an inefficient
Yeah, yeah, it should be a
user, like,
discussion that we do with neuroscience.
yeah.
There is a lot of accuracy, but just thinking about how much information you need to specify the connecton at like that is not zero. That is a lot.